Good evening, everyone. So I welcome everyone on behalf of India March for Science. And today we have an interesting discussion. We have with us Dr. Jayant Murthy. So before I introduce you to the professor, I would just give a brief introduction on what IMF is. India March for Science, or IMFS, is an organization which joins the science communities across the globe to call for science that holds the common good and for policymakers to enact evidence-based policies in the public interest. So this year, we are conducting the march from today, and we also have another program on the topic role of scientists and science in containing COVID. That will be happening tomorrow evening, and we have been doing India March for Science from 2017, and from then on, we have joined the international community to uphold science. So that's a very brief introduction about India March for Science. And with that, we have here Dr. Jayant Murthy. So I'll just give a brief introduction about him as well. So he is a senior professor at the Indian Institute of Astrophysics, also called IIA. Prior to joining IIA, he received his PhD in physics from the Department of Physics and Astronomy, John Hopkins University, Maryland, from the United States, and later joined as a research scientist in the same. His research involves in space missions, starting with a payload on the space shuttle, interstellar dust and diffuse radiation field studies, SETI, which is also called Search for Extraterrestrial Intelligence, and many more. It is worthy to mention that Dr. Jayant is one of the prominent scientists of the country who is popularizing science among the common folks for its deep and better understandings. And we have him today for the same reason, and also on a very interesting topic, the joy of astronomy, which is like close to my heart too. So I have a personal interest in learning the objects in the skies. So without much further ado, I'll request Dr. Jayant Murthy to take over and walk us through what he has for us today. Hello, sir. Over to you.
Thank you, Anand. So I was given this title, The Joy of Astronomy. And so this is a quote from Brian May, who was he was an astronomer before he became the lead guitarist for Queen. And now, of course, he after Queen broke up, he finished his PhD, and he's actually got papers that many of us cite on the zodiacal light. So when we do astronomy, when they ask me to talk about the joy of astronomy, it's a little difficult because for me, it's not that much of a joy, considering that it's my profession. So let me leave this here, and then I'll get back to it at the end, and talk a little bit more about the joy of astronomy. So this is the hallmark of a politician. You give them some topic, and then they go ahead and talk about whatever else they want to, with only a token gesture of what the topic actually is. So what is astronomy? Now, many people they have some confusion. Astronomy, astrophysics, astrology, they all begin with astro for star. So what is the difference? Well, they all study stars and space. In the past, traditionally, astronomy has been an observational science, meaning that you look up and you describe the sky. Astrophysics is the physics of how things of astronomy, why things work. So in astronomy, you look up, you see a star, and you say that star is red, or that star is blue, or white, or yellow. Astrophysics, you say, okay, why is that star blue? Why is it red? Why is there a star at all? And so it's more an explanation, whereas astronomy is the description. Now, in modern astronomy, there are many different fields, the many different parts of astronomy. There's observational astronomy, theoretical astronomy, data astronomy, radio astronomy, UV astronomy, which is my own field. But really, it's become much more of a unified field. Astronomy itself is too large for any one of us to understand much about areas that are not in our specialty. But we all may do a combination of observations. We try to look at the data. We try to look at why things are. So there's not that much difference between astronomy and astrophysics anymore. Astrology now, that's a completely different matter. It is true that we began with astrology in the same way that chemistry began with alchemy. Astronomy began with astrology. So people look up at the sky. For instance, the Chinese have this 1,000-year record of objects in the sky. And why did they do that? They did that because it was important for the emperors to know to predict what would happen in the future. So they did it for astrological purposes. Now in the modern era, astrology is really the province of kooks or frauds. It is now, given that we know so much about the universe, given that our daily lives are filled with science, everything that we do is based on modern science. The computers that I use, that's based on science. The internet that you're watching this on, it's based on science. If science were not at the basis of everything, then modern life would be impossible. There's just no place for astrology in modern science. And so let's go back to the history. Where did astronomy start? It started as a very practical field. We say that astronomy is the oldest of the sciences, and that's because astronomy began with civilization, or rather civilization began with astronomy. When you're a hunter-gatherer, perhaps you don't need to know about the seasons, you don't need to know what the sky is like. You just follow your prey. You're hunting you're hunting mammoths. You follow the mammoths along. So now, what do we? It started in when people switched from being hunter-gatherers to agriculturists. Now it became important to know the seasons. So when is it time to plant? When will the river flood? And they did this by looking at the sky. So when some star rose over the horizon, when the sun was in some constellation, then you know that it's October. Maybe it's time to harvest your crops. If the sun is in some other constellation, now you know it's June, so now it's time to plant your crops. Astronomy was also used for navigation. If you know where the pole star is, for instance, and so based on that, you know what latitude you are. You can roughly tell where you are on the Earth's surface. Now, of course, if astronomy played such an important role in people's lives, then perhaps then here's where astrology began. If the sky is so important, then maybe it's trying to tell us things. Maybe it's not just a messenger. Maybe what it is it's actually causing things. So here you have the tapestries from the Bayeux Tapestry. That's Halley's Comet, just before the Norman invasion of 1066. You have Julius Caesar. When beggars die, there are no comets seen. The heavens themselves blaze forth the deaths of princes. So it becomes, astrology is not just a descriptive science. Now it becomes a predictive science. So when modern astronomy came, probably with all of science is a web. So there's a web of science. There is it's very difficult to ascribe any discovery to a single person. Rather, there's a whole set of discoveries that came about with many different people involved. But of course, when we teach it in schools, we like to have a linear narrative. So we ascribe the geocentric theory to Copernicus. So Copernicus was perhaps the first of the modern astronomers. He lived in the 15th, 16th century. And what he did was he postulated the heliocentric system. Before that, it was a geocentric system. Most people would say that everything went around the Earth. And what he said is that no, life becomes much easier if instead of going around the Earth, everything goes around the sun. And I hope this video comes. What Copernicus did was that he showed that the Earth is not the center of the universe. So there's two main revolutions in modern astronomy, or two main revolutions in modern science. The first of these was the Copernican Revolution, where Copernicus showed that the Earth is not at the center of the universe, rather the sun is at the center. And now what this meant is that you can expand this. Now we know that the sun is not at the center of the universe. Now the sun is not even in the center of our galaxy. Our galaxy is not at the center of the universe. We're just in some small galaxy, or some ordinary galaxy somewhere in a huge universe. There's nothing special about humanity. And so that's what the Copernican Revolution did. The other revolution was, of course, the Darwinian Revolution. Now, after Copernicus came Tycho Brahe. And what Brahe did was he was a superb observer. He was the last of the old observers, the observers who looked at the sky not with a telescope, but with their eyes. And he did it from this observatory in Uraniborg. And I always like to show this because this is such you don't expect astronomy to come from here. Rather, you expect vampires and ghouls to be here. But this is the observatory from which Tycho Brahe observed the sky. Now, what Brahe did was that he observed the entire sky, and he cataloged the positions of all the stars and planets. Now, his student was Johannes Kepler, and Kepler, he took Brahe's data. One might say that he stole Brahe's data from Brahe's family, but he took Brahe's data and he analyzed all of these observations. And what Kepler did was he came up with Kepler's laws. So I'm not going to go into Kepler's laws in detail, but they apply. Basically, what he said is that planets move in ellipses with one focus at the sun, and that as planets come closer to the sun, they move much faster. Now, the importance of Kepler's laws is that they don't just apply to our own solar system. It's a universal law. It applies wherever we look. It applies to the motion of stars around the black hole in the center of our galaxy. It applies to galaxies moving around the center of mass in a huge cluster of galaxies. And so this is a universal law. And what we'll see when we come, let me go through Galileo, and then we'll come to Newton. And what Newton did is he took Kepler's laws and he derived the law of gravitation. Now, after Kepler, or contemporaneous with Kepler, was Galileo. Now, Galileo was the first of the modern astronomers. He looked at the sky through a telescope. In fact, Galileo was not the first person to look at the sky with a telescope. Galileo, what he did was he found he took two lenses made by this Dutch optics maker, and he put them in a telescope. But people had known of telescopes long before. They were used in navigation. They were used to look at ships far out on the horizon. So it's inconceivable that someone didn't actually look up at the sky. And there was even an English preacher who did look up at the sky and describe what he saw. But the reason we celebrate Galileo is because Galileo described what Galileo did was he publicized what he did. He went out into the public square at Pisa and he gave lectures, not in Latin, but in Italian, on his discoveries. And so this points out some of the important factors in doing science. It's not just important to sit and do all the science, to sit and learn about everything. It's important to talk about it. It's important to disseminate your knowledge, to go out and not just to talk about it with your fellow scientists, but also to communicate with the public. And so rightly so, we celebrate Galileo as the father of modern astronomy. And here's one of the things that he did. He discovered the moons around Jupiter. The importance of finding the moons around Jupiter was that it showed that there were objects in the solar system other than the Earth around which objects went. So before that, we knew the moon went around the Earth. What Galileo showed is that the moons of Jupiter also go around Jupiter. And so what this shows is this is just an animation of his own observations. Of course, what he had to do was he had to just plot the points on a piece of paper. And so what this animation does is it takes those points and it animates them on a modern picture of Jupiter, of the moons of Jupiter. So rightly so, we celebrate Galileo as the father of modern astronomy. And as a tribute, 2009, 400 years after he first looked at the sky through a telescope, was celebrated as the International Year of Astronomy. Now, after Galileo came Newton, and Newton was a multifaceted personality. He was knighted, of course, but the knighthood didn't come for his scientific discoveries. The knighthood came because he found he was later appointed Master of the Mint, and he made coins less easy to forge. So he worked on reforming the coinage. But this is from Samuel Johnson. Nature and nature's laws lay hidden night. God said, let Newton be, and all was light. And so what Newton did was he took Kepler's laws, as I said, and he formulated, from Kepler's laws, he formulated the universal law of gravitation, which again applies throughout the universe, at least except when, with the modifications made for special and general relativity. It applies throughout the universe. Now, once the telescope was discovered, now this started allowing modern observations, modern discoveries to be made. And so the first from the time of the ancients, we had known of 5 planets: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. 5 planets plus the Earth. And so once the telescope was discovered, now it allowed the discovery of further objects in our own solar system. And so the first of these planets to be discovered was Uranus by William Herschel in 1781. Now, it had been observed earlier because it is a naked eye object. You can see it with your naked eye, but it was always thought to be a star. But when Herschel saw it through a telescope, it looked comet-like. It was not a star. Stars are points. This was bigger than a star. So at first he thought it was a comet, but then when he followed it along, he discovered that it was actually a planet. And so Herschel was the royal astronomer. His salary was paid by the King of Britain, George III. And so he said, he knew where his money came from. So he said, let's call it Georgium Sidus, George's star. But of course, no one outside Britain liked that idea. And so then after a few years, people converged on Uranus. All the other planets are named after Roman gods. And so it's only natural that Uranus also be named after a Roman god. Now, after Uranus, they followed Uranus's orbit along, and what they found is that every few decades, the orbit looked like it would change, meaning that that they knew all the planets before it. They knew how it should go around the sun because of Kepler's laws and because of Newton's law of gravitation. But when you apply that, it somehow didn't work for Uranus. So why was that? So these two people, John Couch Adams in Britain and Leverrier in France, they said, okay, there must be another planet there. Why is Uranus not going in according to Newton's laws of gravitation? Well, it must be because there's another planet there. And so what they did was they both calculated how heavy the planet should be and where it should be. And Leverrier was the first to tell his friend Galileo at the Berlin Observatory, the newly founded Berlin Observatory. And he said, look here. And if you look here, you might see, or you should see, this planet that I've discovered. And so Galileo looked, and in fact, and he found that planet where almost exactly where Leverrier had said. And so that was the first planet discovered not by observations, but discovered by the point of his pen. Again, as I said, the science is a web of things, and many things are discovered earlier, but maybe not noted. Maybe their importance was not noted. Maybe they were not placed in the context. And it turns out that Neptune was actually in one of Galileo's observations. But because it was, it looks like a point, because it moves so slowly, Galileo thought it was just another star. And so Neptune was discovered by Leverrier and then later by Adams, and first observed by Galileo. Now, even after Neptune was discovered, there were still thought to be errors in Uranus's orbit, and so if the orbit of Pluto was, if the orbit of Uranus was different because of Neptune, and if Neptune still doesn't explain Uranus's orbit, then it only makes sense that maybe you think of another planet. And so they predicted that there would be a ninth planet, and Percival Lovell, who was he was a wealthy man, and he first got astronomical note because he claimed to see the canals on Mars. In fact, he had a whole history of Mars. He said that the Martians first lived near the poles, but then they had to migrate to they lived in the equator, and as water dried up near the equator, they had to make canals to bring water down from the poles, because they knew that these white patches on Mars, which they assumed to be ice caps, shrunk and expanded. And so Lovell was famous for that, and then he searched for this planet X, this 10th planet. And when he died, he left $1 million to continue the search for this 10th planet. Now, his wife didn't like the idea, so she fought about it in court. But finally, everyone settled, and the money was used to fund the Lovell Observatory in Flagstaff. And a young astronomer, Clyde Tombaugh, discovered Pluto in 1930. Now, when they discovered Pluto, this is the discovery photograph, and someone helpfully put arrows here so that you could see where Pluto is. It's just a lesson. If you're looking up in the sky and you see an arrow, that whatever the arrow points to must be interesting. So the two arrows show Pluto on the two different days, January 23rd and January 29th of 1930, 6 days apart. Now, once they found these two, Now they knew they could track Pluto's orbit. And so they went back and looked at old photographs, and they discovered that, in fact, Pluto had been observed for ever since 1900. But again, it's so small, it's so faint, people thought it was a star. And so this was the last of the planets, Pluto. Now, of course, there's the whole controversy about whether Pluto is a planet or not. And we know that there's further objects, even further than Pluto. But I won't get into all of that. So this was the discovery of Pluto. So what do we do now with astronomy? Now we use telescopes. The telescopes let us see much deeper into the sky. And so when we were doing naked eye astronomy, you're limited to maybe 6th magnitude stars. Once you have telescopes, now you can go that much fainter. So the telescopic observations, of course, as I said, began with Galileo, and now you see so much more detail in the sky. You can see fainter. Once you go out into space, I'm sorry about the colors here; they got washed out. But so you can see much deeper. Now you combine this with photography, and now what happens is that before you had to record things on a piece of paper. So you have Galileo. Galileo looks at the sky. He takes a piece of paper and he draws what he sees. Now you have photography. So it's not just that that you look up at the sky and you draw what you see. Now you preserve what you see. So this here is the first picture of the moon, taken by John Draper in 1840. It was a daguerreotype, the early photography. Now, of course, we have much better instruments. We don't do photographic film anymore. Now we use CCDs. In the optical, in the X-ray, we have other detectors, and UV, we have other detectors. But nevertheless, we record the data. So what does modern astronomy do? Astronomy, I think I said at the beginning, is a data science. It's unique amongst all the sciences. Most of the sciences, you can do experiments. So you do an experiment under given conditions. Maybe you change those conditions and you do another experiment. And you can try to track down which of your changed conditions leads to changes in your experiment or changes in your results. But astronomy, you can't do that. You get what you see. You look up at the sky, you observe data, and you get whatever you get. You can't go and blow up a star to see what it looks like. You can't increase the temperature of the sun by 100 degrees and see if life is still possible on the sun. You get what you get. The sky is the way the sky is. And so now, with telescopes, we now have we now can see much deeper than we used to be able to. We can see out to the edge of the universe. With photography and other modern instruments, CCDs and so on, we have a record of what we see. So it's not just dependent on my drawing abilities or on whether, like Percival Lovell, I had been staring at Mars too long and I saw these lines on Mars. Now things are subject. There's no whatever I observe is preserved for all eternity. We extend this not just to optical telescopes, but we have radio telescopes. These are the GMRT telescopes near Pune. We go out into space. This is the canonical picture from Apollo 8 of Earthrise. Buzz Aldrin would later call the moon the magnificent desolation. This particular picture became a hallmark for the environmental movement. It showed that there's nowhere else to go. The moon, we can't live on the moon. All we have is this big blue marble, the Earth. All of life is on the Earth. all these dreams that Elon Musk has of sending millions of people to Mars. I mean, it's not going to happen. Mars is not a nice place to stay. Really, the Earth is all we have, and we need to make sure that the Earth stays livable, and that's what this photograph shows. The Earth is all we have. In the blackness of space and the desolation of the moon, the Earth is all we have. And when we look at the temperature, the global temperature rise, they said we have to keep it under 2 degrees. I don't know if that's going to be possible. Maybe 3 degrees, maybe 4 degrees. We can all see how the climate has been changing. From the extreme events, the fires in Greece and Turkey, the floods in China, the droughts in the U.S., in Bangalore itself, our weather has been quite unusual the last 2-3 years, and so this is what we have, the Earth. And when we ruin the planet we have, I mean, where else are we going to go? So let me show a couple of science results. This is what as I said, we extend astronomy. So we started out with looking from our eye. We started out by writing on a piece of paper. Now what we do is we go out we look at other wavelength regions. We look at radio telescopes. Radio telescopes allow us to look at the coolest objects in the sky. So this is things like the beginning of the universe. When the universe began, it was small and hot. Now the universe is big, and so conservation of energy, it's become cold. So what do we see? We see the leftover radiation from the Big Bang as the 3-degree microwave background radiation. And that's what this plot on the left shows. I was actually at the meeting where it was first presented. This was at the American Astronomical Society in Washington. And when this plot was showed, everyone stood up and gave it a standing ovation. One of the few times you see astronomers give a standing ovation to a talk. And what this plot showed is that the sky, when you look out at the sky, the background radiation is at a temperature of 2.725 degrees Kelvin. Exactly. It's a black body curve. Don't worry about what black body is. Just know that when you get a black body, that tells you exactly what the temperature is. And so here's the temperature, 2.725 degrees Kelvin. And so what this shows is that there is nothing else that this could come from. Before that, people were talking, okay, maybe steady state theory, maybe the universe was always there. It started before time began, ends when it exists on to infinite time. But what this plot showed is that there was a beginning to the universe, and that beginning was the Big Bang. So that's this plot on the left. And this particular experiment, the COBE experiment, got 2 Nobel Prizes. John Mather, who's now the project scientist for the Space Telescope, for the James Webb Space Telescope, and George Smoot, who you may remember from the Big Bang Theory. Yeah, I think he was on 2 episodes of that. And the picture on the right is the Eagle Nebula. And what this is giant clouds of gas and dust that are in space. And so you see them, they're dark against the more distant background. And in those clouds, you can see these bright stars. You can see these red stars. Those stars are not actually red. They're actually blue stars. The reason they look red is because we're looking at them through so much dust. So they've been reddened. Just like the sun, for a different reason. The sun looks red when it goes down to the horizon. The reason the sun looks red is because of Rayleigh scattering from molecules in the atmosphere. But you might note on a dusty day, the sun looks exceptionally red. And so the reason for this is because the short wavelength light is scattered off from the dust grains, and all that comes through is the long wavelength light. And so these stars look red. So these are not actually red stars, they're blue stars. Blue stars means they're very young, hot stars. So these are sites of stellar formation. So when you look at the Eagle Nebula, what you're really looking at are stellar nurseries. This is where new stars are being formed. Our sun formed perhaps in a very similar environment 5 billion years ago. Now, when I was a graduate student, there were no planets outside our solar system. The first extrasolar planet was discovered, if I remember right, in 1989 or so, a couple of years after I finished my PhD. The planets first started being discovered on a regular manner, perhaps around 1992, 1993. And this got the Nobel Prize a couple of years ago. But after the launch of the Kepler mission, now we see planets everywhere. And so this has completely changed our understanding of planetary formation, even of life. Before, what we did was we looked up and we had our solar system. And our solar system is pretty easy to understand. You have the hot rocky planets near the sun. You have the cold gas giants far away from the sun. Now, when we look at Kepler, it turns out that our own solar system is an anomaly. Most planetary systems are nowhere near as easy to understand. Most planetary systems are much more complex. You have these hot Jupiters, Jupiter-sized planets that are orbiting closer to their parent sun than Mercury is to our own sun. How did they get there? Well, most likely they formed far away, and they were broken loose by some event, maybe an interaction with a passing star, maybe interactions with other planets. And somehow they came closer to the sun, to their own star. And then because of dynamical friction, because of interactions with the orbits of the other planets, their orbits became circularized. And now they're orbiting very close to their own star. So again, as I say, when I was a graduate student, there were no other planetary systems other than our own. And so when Frank Drake put together his Drake equation, which tried to predict how life was in the universe, how common life was in the universe, he said, okay, maybe only 50% of all planets have, 50% of all stellar systems have planets. We know that's not true anymore. Now we know that every single star in the sky has multiple planets. Even more than that, there are more planets without stars than stars with planets. So there's a whole lot of free-flowing planets. Planets are everywhere. And this came from the Kepler mission. This came from a space observatory. So what do we have now? So now we're in this regime where astronomical data is increasing by leaps and bounds. It started with Galileo and his few handheld sheets, hand-drawn sheets. He wrote in his notebook, he stuck in his drawer. We went on, people described what they saw through telescopes. Then you had the photographs. People would stick their photographs in their desk drawer and look at it later. But it's all small amounts of data. Now we have large telescopes. The large telescopes can see so much fainter. They see so many more objects. And we have large detectors that can store enormous amounts of data. And so we have a flood of data now. We have too much data. So we now have to find new ways of looking at this data. Now we have we have to develop new techniques. We have to bring in techniques from computer science. We have to know detailed statistics. And even more so, this gives an opportunity to amateur astronomers. Again, people would look up at the sky, and whatever their telescopes were, no matter how good their amateur telescopes were, they were nowhere near as good as the professional telescopes. And so now we have all of the data that's taken by astronomers is now open to the public, whether it's from ground-based observatories or space-based observatories. And so here is new ways for people to get involved. Of course, there's still barriers. There's still ways. You have to know how to get to the data. You have to know what to do with the data. You have to know how to interpret the data. But these are all surmountable. If people can actually sit at home with the computer and with an internet connection and get access to the latest data and the latest results. And so this does allow for the growth of citizen science. Some missions have embraced this. So, for instance, the Kepler mission, they want to search for planets, and they have all sorts of automated algorithms to search for planets. The trouble with automated algorithms is that they're very good at finding what you know exists. They will find planets that look like the planets you want to find. So what they did was they opened up their data. They released it to the public, planethunters.org, and people could look at the data and they could try to analyze it themselves. And there have been planets, I think Tatooine, the stellar system with two suns, I think that was found by an amateur astronomer. The other one was Galaxy Zoo. The SDSS project, again, they have so much data, they can't possibly look at all the data. So what they did was they had a project Galaxy Zoo, and they told people to look at galaxies and to classify galaxies. And someone said it's like eating, the guy was an Englishman, so he said it's like eating crisps. You can't stop at just one. You identify one galaxy, and then you identify the next galaxy and the next galaxy, and you say whether this is a spiral galaxy and whether this is an elliptical galaxy and so on. It turned out, just as a sidelight, that there was an interesting insight into the human brain from this. They found that people were classifying more galaxies, I think it was clockwise than anti-clockwise. And so this doesn't make sense. Why does the universe care whether your galaxies are clockwise rotating or anti-clockwise? It turns out that the human brain is better at seeing clockwise galaxies than anti-clockwise galaxies. So science is not siloed. Many times we look at science and we say, okay, this is only this one area, and it doesn't apply to everything else. But science is broad-based. You can never tell which part of what you're learning will impact some other field. So let me go back to Brian May's original quote: "Astronomy is much more fun when you're not an astronomer." Now, as I said, and as I'm sure you know, Brian May, he was a PhD student before he became the lead guitarist from Queen. He discovered that there was much more money in being the lead guitarist for Queen than in astronomy. And so he quit astronomy to do, and you can't do both. You can't be the lead guitarist for Queen and a professional astronomer. So he quit astronomy and went on to be the Queen guitarist. Once he retired, or once Queen ended, Freddie Mercury died, of course, and he got his PhD, I think about 10 years ago. And now he's gone back to becoming an astronomy enthusiast. He was in the New Horizons control room. He's visited the Rosetta mission. The Rosetta mission, by the way, they use his original papers. He was working on the zodiacal dust, and so they referenced Brian May's original papers. So what does this say about astronomy and it's true about all of science? I say joy of astronomy. I say astronomy is much more fun when you're not an astronomer. But this is true of everything. If it's not your profession, then it's more fun. If you're just learning about it just for the sake of learning, you have a lot of fun. You learn facts. Facts are interesting. You're learning about how the world works, and this is you surprise your friends. Hey, did you know that that people run experiments with little cones around cockroaches, so that to see how their antennae work? So you find out all these fun facts. So that's for amateurs. And as I said, now people can actually look at astronomy or look at astronomical objects. They can download Hubble pictures, They can play around with Hubble pictures to make them more beautiful. They can try to bring out the giant red spot on Jupiter. On Jupiter, they can look at Jupiter's moons and watch them rotating. You can look at the volcanoes on Io. You can look at Titan. So there's all these neat things that you can do looking up at the sky or using astronomical data. So what I wanted to talk a little bit about, maybe a couple of minutes about, is why I do science, why I do astronomy. Now, when I've always been interested in science from the time I was a little child, 5 years old maybe. We used to get these little ladybug books, and I would read the ladybug books, and they were aimed for small children, 5 years old, 6 years old, and they would describe how stars work. They would describe how grasshoppers jump, all these things. And so that's how I started in science. When I was 8 years old, Neil Armstrong landed on the moon, and that was a seminal event. Neil Armstrong landing on the moon. How many times do you get to see someone land on another world? So from that time, I always knew that I wanted to learn about the universe. And how do you learn? You do science. In the modern era, you need a PhD, so you'd have to get a PhD. So I knew I needed to get a PhD to do science, and that's what I did. Now, when you're now when you're a student, that's fun because you're learning about new things, you're learning about new techniques, you're learning how to do things for the first time, and so all of this is great. You have a lot of fun as a student. Of course, I also did a lot of other things. I wrecked my knees by playing basketball, but whatever, you have a lot of fun learning. It's all about the learning. So what is when we're doing science, what the important thing is not the end result, it's the journey. It's not the actual discovery, although that's great. You suddenly have an epiphany and you say, hey, this is how the universe really works. All along I'd been thinking, here's Kepler thinking that everyone before Kepler thought that the planets went in circles. It took the genius of Kepler to say, no, the planets are not moving in circles, rather they're moving in ellipses. That was a seminal moment. Again, it was a paradigm shift. Kepler had this epiphany now, and that must have been such a brilliant moment for him, such a joyous moment. Okay, now I understand. People were wrong all this time. All these thousands, millions of people before me, thousands of people working on this, they were all wrong. I now know how it works. And so that's part of the joy of doing science. You're doing something new. You're discovering how the universe works. Every day that you go in, you may not make much progress. It's frustrating. You go into all sorts of wrong steps. But what you're doing is you're still learning about how to do things. You're learning techniques. You're saying, okay, no, maybe this is not right. Maybe this is right. And then finally you finish and you say, okay, now I know a little bit more about the universe than I used to. And so that is the joy of science. When you find out more, when you make a little go, when you stand on the shoulders of giants, and you see a little bit further than they did. So that's what I'll end with. That's the joy of science, not just of astronomy, but of all of science, of all of academics. And that's why academics is important, because it gives us an insight into the world around us. So let me end here, and happy to take questions.
Thank you very much, sir. That was a very insightful. That was very insightful talk, and I personally enjoyed it a lot. You have told us, like, right from the dawn of civilization, how the heavenly bodies or the sky in general has helped the growth of human civilization itself. But as a timekeeper for the agriculture during the advent of agriculture, and also later for the growth of science, as well as the human knowledge in general, how the heavenly bodies or the sky in general or the night sky helped us. So with that, there are a few questions from the chat from Facebook we have got. I also urge others who are watching to go ahead and put their questions in Facebook. We'll have Professor Jayant Murthy um, answer your questions. So I'll go with one of the first questions that we got when we started the session. So G. Satish asks, did Indian astrology originate in India?
Say that again.
Did Indian astrology originate in India?
All right. Now, this is a difficult question for me to answer. Astrology really began with the Babylonians, right? And so, who knows what the interaction between the different people were? Of course, now the modern zodiac that came from the Greeks. So when Alexander came, he brought the constellations. He brought the sun being in this constellation in the sky and so on. That came from the Greeks. But I know so little about astrology that I couldn't really tell you. There's so much good science in the world that I always like to focus on the science. I'm interested in history, and so this is actually a good question. I'm interested in how astrology plays into calendars and things like that, but I can't answer that question authoritatively.
Okay, sir. Yeah. Thank you, sir. And it's another comment, or I'm not sure if that a question. We should discuss more about how the day-to-day life is affected. Probably what I sense from this question is like there is a sense that the research in general or in astronomy are not connected with the questions of the society, right? So can you shed some light on like how the research that we do in the that you do in the laboratories, how does it help the society?
Yes. Now, of course, there's what I would like to stress all along is that uh, there are many. When you ask a politician, what the politician will tell you is that you have to do research that, as you say, impacts society. You have to work on the problems of society. Now, of course, astronomy doesn't do that. We don't impact on society. So this is a broader question. What is the need for academics at all? Why shouldn't we all just have little private labs? So now the canonical answer to that is that we don't know what today's discovery is that will impact our lives tomorrow, whether it's X-rays or the laser. These were all basic science. Now we cannot imagine modern life without things like X-rays or lasers. So that's one answer, but I think it's a little deeper. I think that what we're trying to set up is not a system where we where you have academia focusing on things like on better cars or better phones or solving the agriculture crisis. Yes, academics can play a role in this. Yes, there are people who study all of these. Yes, there are people who work on malaria, finding cures for malaria. But the real the real goal of academia is to provide an environment where people are encouraged to learn. You set up an environment where people are able to learn and think of new ideas. So if you say that everyone should only focus on problems of today, all you will do is you'll solve the problems of today. You're not going to change the future. Now, what you really want to do is you want to say, okay, I am going to teach how to think. I'm using astronomy as an excuse to teach people how to think. I'm using history as an excuse for teaching people how to reason. Now, once you do these, I'm not going to be the one to solve this. But it's out of academia that you get, not that Facebook but I mean, look at the reach of this program. The reach of this program in Facebook is much greater than if I had gone to 100 colleges and talked. And this all came out of universities. It's no accident that Facebook came out of Harvard. No accident that Microsoft came out of Harvard. It's no accident that Silicon Valley is from Stanford. It's no accident that Bangalore is the high-tech city, the capital of India, because it's all because of academia. Bangalore because of ISC, Silicon Valley because of Stanford, Microsoft, Facebook because of Harvard. So you have to have these academic environments where people are free to think, where people are free to learn. And it's only out of that that you get the solutions, not just to the problems of today, but to the real problems of tomorrow. I hope
Sure,
that
sir.
answered the question.
Yeah,
I mean,
yes,
even
really
on
you did.
the academic term, I mean, purely on purely economic terms, there have been studies that show that this was an Australian study, every dollar that went into research paid for uh, gave $5 back.
Okay. So in the same context, right, you mentioned like how the current understanding of how the planetary system worked in the case of Neptune, how it helped us predict where the next planet was, right? But the
Mhm.
opposite also happens, right? So when we run into some anomalies, like the same was extended to Mercury also. So the Mercury also was not, Mercury's orbit was also not fitting into the then understanding of the orbitary motions. And I think, if I'm not wrong, they're searching for another planet between Mercury and the Sun, which was called Vulcan. If I'm not wrong, you can
Absolutely.
correct me. So that little anomaly led to uh, new science itself, right? The relativity. I mean, the rest is history.
Mhm.
How relativity helps us is history. So these little anomalies that we end up in science also enriches our understanding of science further, which is also helping the society as well, right? So we have to keep on running into these kind of issues again and again to enrich our understanding.
So without relativity, the GPS would not be
Yes,
possible.
yes,
You could not
yes.
call your Uber without
Yeah,
without relativity,
yeah.
because
The same
the
phone that is
satellite
being,
is incorrect.
yeah, the same phone that's being used to put the question would not exist without GPS,
Yes,
right?
yes.
So there are a lot of applications that relativity has, which was a direct result of what was going on in the field of astronomy. Okay, so thank you, sir. Thanks for that. And there is one question. What is the smallest star in the universe? Is it Proxima Centauri? Is there any criteria?
Well, now it all depends on what you call a star. So the Proxima Centauri is a main sequence star. It's a faint red star. So it is a very small star. But uh, so what we call a star is something that has nuclear fusion. If it's got fusion in the center, it's a star. So Proxima Centauri is probably close. I think that's something like a tenth of a solar mass, if I remember right. If you get less than a tenth of a solar mass, you can't have nuclear fusion in the center. So probably it's close, but
Okay,
the smallest star in the universe, I can't tell you.
okay. So there is no clear demarcation like when
No
a
clear
planet
demarcation.
becomes a star. Yeah, okay,
It's a continuum. That's right.
okay. So there's another question from the Facebook, Kumar Shetty. So recently we saw a halo around sun from Bangalore. So he is asking us like share some information on that, how it happens.
Yeah, that was a beautiful picture. Unfortunately, I didn't see it, and I'm kicking myself. I saw all the messages, but after after it was gone, and so that's just ice crystals around in the sun's in the Earth's atmosphere. So it scatters the light from the sun at 23 degrees, and so you can see these halos around the moon also, and that I have seen. But that sun one was really spectacular.
And there's what Sudha Suresh is requesting if you would recommend any books to read on the lighter aspect of astronomy. Probably she
The
means like for
lighter aspect.
beginners.
Yeah. Yeah. So let me break that up into a couple of questions. The some of the excellent books to read, not just on astronomy but on science, is George Gamow, Gamow, and he's written a bunch of books on Mr. Tompkins. These are old books, and I don't know. They may even be free to. They may even be on Gutenberg now, but those are very good. I don't know of many books on the so-called lighter aspects. I do read a lot of popular books. So especially my main interest is in biography. So I read First Man, the Neil Armstrong one. I like the astronauts books. The last one I read just a couple of weeks ago was what's it called, Beyond, and that's about Yuri Gagarin. So these books are the kinds of ones that I read. I don't know much about the lighter aspect, but any suggestions, I'm happy to to read also. By the way, a good introductory book to astronomy is Eric Chason. A little expensive; it's about 4 or 5 thousand rupees, but it's very good. Chaisson.
Okay, thanks, sir. Suresh Purohit is asking to share some information on black holes.
Uh-huh. Oh, black holes. Okay. I mean, there's uh, it's a very broad topic on black holes. So what is a black hole? It's just a place where gravity is so strong that nothing, not even light, can escape. Uh, so you have a lot of mass. It has to be something like I mean, okay. There's different sizes black holes. You can have the very small black holes that formed at the beginning of the universe. These are the what are they called, the micro, whatever they're called, micro black holes, nano black holes, whatever they're called, and these last only a few seconds or a few milliseconds. And you have the stellar mass black holes, which are formed from individual stars. You have very large stars. So when the stars explode, what is left in the center is so massive that they collapse and under the force of gravity, and there's nothing that can stop it. So so you have stellar mass black holes. You have the very large black holes, the LIGO observatory found. These are some 30 mass black holes, solar mass, 30 solar mass black holes. These were formed by collisions from other black holes. And you have the supermassive black holes that are in the center of galaxies, which are formed by the collapse well, I mean, who knows how they're formed? Perhaps by many different stars or black hole or collapse of black holes. And so the basic thing about all of them is that they're so strong, the gravity is so strong that that the escape velocity is greater than the speed of light. In essence, what really happens is that space is curved, and so that as a light photon leaves from the black hole, it's curved back into the black hole. So that's the basics of black holes. And of course, there's so much more to talk about. It's a whole separate talk. But any specific details, perhaps you can ask.
Thank you, sir. So, in the session, you echo.
I'm sorry, I missed that. Okay, I think we
So
lost
can you
you
hear
for a
me?
bit back. Yeah.
Okay, okay. So there's one more question from the Facebook. I'm not sure. I'll just read it. So the question is, sir, can we observe a gravitational lensing? Sorry, I lost it. Sorry, I lost the question. Just
I think you're breaking up a little.
can you hear me okay now?
Yeah, got it.
Oh, sorry for that. So the question is, sir, can we observe gravitational lensing around a black hole candidate star?
Oh yes, you can observe gravitational lensing around anything, any object. You can observe lensing around planets. And so people have actually done this. What's the name of that project? It's a micro lensing project. Yeah, can't remember the name. No, anyway, whatever it is, it's a micro lensing project. And so what they do is they look at the Magellanic Clouds where there's a lot of stars, and they see these little blips in the data, and that happens when the light from that star is lensed around a planet or a star in the line of sight. And so they've actually seen, this is how they discover planets that are not around stars, by these little micro lensing objects, micro lensing events. So yes, you can observe gravitational lensing around anything, and certainly around large stars, small stars. It's just that they have to be, you have to be placed just right. They have to be right in the line of sight, and many of these micro lensing events are so short that they're hard to observe. But yes, you can observe it.
Recently, I was just reading through some document. I mean, going through a YouTube video where it was mentioned that we are trying to identify rogue planets which are not part of any solar system using the same technique, micro lensing, when it passes.
Exactly. Those were micro lensing events.
Yeah. So there's another question on black hole radiation. What is black hole radiation? A lot of people are interested in black holes.
Yeah, of course. Black holes in cosmology. That's always the draws.
So the question is on black hole radiation. He's asking, what is that?
Oh, I'm sorry. What is black hole radiation? So what happens is that near the edges of black holes, you have the uncertainty principle, the Heisenberg uncertainty principle. What most people know it as is that position and velocity, position and speed, you don't know at the same time. But what this is that you have the energy from the black hole. You get, because there's so much energy around it, you get a creation of a positron-electron pair, typically a positron-electron pair. One part of that pair goes into the black hole, the other part escapes. And so this is, and then once it escapes, if you're getting a positron escaping, now that will then decay pretty fast, and you get a gamma ray out. So this is this Hawking radiation. It's radiation from around the edge of the black hole because of the uncertainty principle. Now this energy comes from the black hole, and so the black hole will evaporate. If you have a very large black hole, the energy that's evaporating is a small part of that whole thing. And so the black hole will last for trillions of years. I mean, much longer, very long time. If the black hole is one of these very small black holes, tiny black holes, then the radiation is quite large compared to the energy of the black hole. And so the black hole doesn't live very long. it explodes in a burst of radiation. And so that's all it is. It's just because of the uncertainty principle, you're getting antiparticle creation around the black hole, and the energy from that is coming from the black hole.
Okay, sir. Okay. So, in your talk, you mentioned like uh, Earth is the only planet we know that life exists, and we should take care of it. Definitely, we should. And I saw from your profile that you're also part of the SETI group. Would you like to
No, I'm not part of
comment
the SETI
on?
group. It's just one of my interests.
Okay, okay. So, would you like to comment on extraterrestrial life, not just intelligent life, any extraterrestrial life? And there has been some fuss around probably few months back when there was phosphine identified in the Venus's atmosphere. So, would you like to give some insights into like where we stand with our understanding of life other than us?
You know, the universe is so big that it's inconceivable to me that there's not life elsewhere, and even that there's not intelligent life elsewhere. I would say by the Copernican principle, what does the Copernican principle state in essence? It states that we're not special. And so how are we special now? Well, we're the only intelligent life in the universe. And so that to me, that just doesn't make sense as a philosophical uh, sentiment. So to me, I believe that there has to be life out there somewhere. And moreover, I believe it has to be intelligent life. Now, whether we will ever contact that life, that's an entirely different question, because now physics gets in the way. We have relativity. The speed of light is slow compared to the size of the universe. So will we ever be able to contact extraterrestrial life? I don't know. Now, as a special case, there's quite possibly life on Mars. There's quite possibly life on Europa, which is the moon of Jupiter with the underwater ocean. There's possibly life on Titan, which is this moon of Saturn with the Titan chemistry. I mean, with the methane chemistry, nitrogen chemistry. So I think it's a far from answered question. But do I think that there's life elsewhere? Yes, I think it's unquestionable that there's life elsewhere. Do I think that aliens have visited the Earth? Absolutely not. I don't think that there have ever been any, quote unquote, UFO. Of course, there are UFOs, unidentified flying objects, but no flying saucers.
Okay, okay. But with our understanding with the understanding that you shared that we are also looking for life on the moons of other planets. So will that change where we are looking for life elsewhere? Like we have a Goldilocks zone that we have defined where we are looking at, right? So this might change the understanding, right?
One of the things that we do is that because we exist, we know that we exist. And so that colors the way that we look at everything else. It colors the way we look at all these scientific problems. So how do we search for life? We search for life that exists in planets that are like ours. Just 1 second, I've run out of, okay. So we search for, let me close my open office session because it says I've run out of memory.
Sure, sure.
Okay, got it. Oh, hopefully this will help. All right, so we search for life that look like ours. We search for life that looks like that needs water. We search for life that needs oxygen, and so on. But maybe there's other forms of life. We can always make arguments. I've seen arguments for saying that you need a moon to have life, because what the moon does is it stabilizes the Earth. If it didn't stabilize the Earth, maybe the Earth would rotate all around the place, and maybe, whatever. We say that we need water. Why do we need water? Because water is a universal solvent. It gives you a place for things to mix. We need carbon because carbon forms so many covalent bonds. So all of this we can say, but But when it comes down to it, no, there's so many different things that we can imagine. So we search for life that we know. Otherwise, it becomes science fiction. If we do things that are far beyond, I mean, you can always say, there has to be silicon-based life, but we don't know how that would form. So that's the only reason. We search for life that looks like what we know.
Sure, sir. And we are approaching the end of the session, and I guess you have answered all the questions that has come in the Facebook as well. And for those, we'll also upload this video in YouTube, so it will be permanently available. You can go back anytime and look at this session. And with that, thank you very much, sir. That was a very insightful talk. Something of very interest personally to me as well. And you gave historical insights to how astronomy has influenced civilization, the growth of knowledge, and how it is still continuing to do so. And once again, I thank you very much, and I thanks everyone who is part of who has watched the session over the Facebook and the other channels as well. Thank you, sir.
Thank you.